So welcome back. So in the previous lecture we introduced this Schwarz space. Yes, and its dual, so space of tempered distributions. Yes. Okay, so we have all seen that this is contained in LP for all P, okay, in 1 infinity. So in particular, this S is in L1 intersection L2. Okay. So therefore we can define the Fourier transform. So Fourier transform on S. Okay. So the usual definition, because it's in L1. So if phi belongs to S, so phi cap j, the usual definition. So phi x okay. So since the elements of the Schwarz space are infinitely differentiable, okay, so we can differentiate under the integral sign and put any polynomial. That also becomes so you have to verify few things. All the time I cannot write that. So if P is a polynomial, then this phi going to P phi. So this is just multiplication. So you multiply the function phi by polynomial. So this is from S to S is linear and continuous. And similarly, the operation of derivative. So phi going to d alpha phi. So all those things, they are very easy to verify. Okay, so as and when needed, you should be able to do that. So we can do the similar thing here. So we just say, so these are the properties of the Fourier transform. We have already seen for L1 functions, but here for the functions in the Schwarz class, they are infinitely differentiable, and any derivative is in the Schwarz class, and if I multiply by a polynomial, again that's in the Schwarz class. So they are all L1 functions. So the operations here are much simpler compared to L1 functions, because L1 functions we have to assume these additional things, but here they are part of the definition. Okay, so we have this. Phi cap j, and similarly if I take multiply by polynomial and then take the Fourier transform. So this is I alpha, I mod alpha, d alpha phi cap. Okay, so if you combine these properties, what we see is the Fourier transform. So let me just call it f, f from S to S is linear. Of course, linearity just comes from the integral, continuous, 1 1 and on. Okay, so this one also comes from the Parseval relation. We have already derived it for functions in L1 intersection L2. So we also have this. So since I am using the subscript m for the norms here, so let me just write L2. Okay. So you just simply use these properties. Though this is not a norm linear space, we still have this 1 ontoness. Okay. So this is very easy to verify. Okay. And now using this property of the Fourier transform on S, we can just lift it to S prime. Okay, so here is the definition. So if T is a tempered distribution, its Fourier transform denoted by T cap is defined by so again we want this to be a tempered distribution. Okay, so I have to define the action of T cap on an element in S. Okay, so this is the definition. So T acting on phi cap. In a moment I will explain the motivation behind this definition, but first let us see the definition makes good sense and it's linear and continuous. Okay, so that's so we have already seen. So the definition is makes good sense because of this property. Phi going to phi cap is from S to S is linear and continuous. Okay, so again that phi cap belongs to S. So T acting on that phi cap makes sense. So this definition makes good sense, and then all other properties are easily verified. T cap is linear and T cap is continuous. So in fact, so that implies, so this T cap is also okay. Such a thing was not possible for distributions. For example, if you take AC infinity functions with compact support, certainly we can define its Fourier transform, but then the Fourier transform will not have compact support. Okay, so in fact that's a big result leading to Paley-Wiener theorem and Heisenberg uncertainty principle. So which states that so only one of the two functions phi and phi cap can have compact support. Both cannot have compact support. That's the crux of the Heisenberg principle. Okay. So such a definition was not possible for a general distribution, and because of this additional property enjoyed by the functions in Schwarz class, we can lift the definition of Fourier transform to the space of distributions, tempered distributions. Okay. So we have to first clear some ambiguities. Okay. So and also this motivation. So motivation is here. Okay. So this a very easy verification using Fubini's theorem. So nice application of Fubini theorem. So suppose F and G are L1 functions. Okay. Then this f g f, let me write that, g cap x dx, f cap x gx dx. So, very good application of Fubini theorem. So, I will just leave it as an exercise. Okay. And this is the motivation behind this definition. So, if we treat this f and f as a tempered distribution, and so in particular I can take G to be in the Schwarz class. Okay. So, this becomes the right hand side and that becomes the left hand side. So, this is the motivation for that definition. Okay. So, this is just an application of Fubini theorem. Okay. So, now our next task is we have to remove some ambiguities with this new definition. Okay. So, we have already seen that LP functions are in the tempered distributions. So, in particular the functions in L1 and L2 are tempered distributions, and they have this definition, new definition of the Fourier transform, and we also have the old definitions being in L1 and then by density arguments in L2. So, we should verify that those definitions coincide with this new definition. Okay. So, let me just do that because that is important. So, with so suppose f is in L1. Okay. So, there is so let me write then f identified with Tf is in S prime. So, as such it will have its Fourier transform. Okay. So, let us compute that and verify that it is the old definition of the Fourier transform. So, T f cap phi, this is the definition. So, this let me do it carefully. So, T f phi cap. So, phi is in S, phi is in S, and this is the definition. Okay. And now you use this one. Just now I said that f p cap, if f is in f and phi are in L1, this is same as f cap. Seen above. Okay. So, as f and phi both are in L1. F is in L1 by hypothesis and phi is in L1 because phi is in S. And this is, we have identified this as, so just T f cap of phi. So, that implies this new definition of Fourier transform coincides with the old one. as far as L1 functions are concerned. Okay. So, for L2 functions we still do not have this kind of thing, but we will argue in a slightly different way. Okay. Okay. Now, suppose f is in L2, okay, and that implies, again let me write that Tf is in S prime. So, therefore, Tf Fourier transform is, by again definition, this is phi hat and this is just by the definition f k p. Okay. So, now f is in L2, phi cap is in S, so phi cap is in also L2. So, this implies, so Tf phi is less than or equal to this f in L2, phi cap in L2. But by partial relation, so we have this f of L2, it is very important. Okay. So, Tf is a linear operator from S into now L2. No, this is a linear mapping from S to C, so linear functional, which satisfy this estimate. Okay. So, since D is in S as a both as a set and also as in topology, so continue, this is the inclusion and this is in L2 for example, and this is dense, this we have already seen. So, S is in also dense in L. So, S is also dense in L2. So, therefore, Tf cap using that estimate, Tf can be extended to L2 as a linear functional. Okay. So, what we get is, so this Tf, let me use G, for all G in L2. And now by Rees representation theorem, by Rees theorem, Tf cap can be identified with an L2 function. Which we denote by f cap. Okay, so that too we denote by f. Okay, and then you do some jugglery with that, so you exactly get that f L2. So the partial relation also. So you get one side inequality here, the other side is also similar. So you also get this partial relation. So as far as the functions in L1 and L2 are concerned, this new definition of the Fourier transform as a tempered distribution also coincides with the old one. Okay. So let me just give some more examples. So what are the what type of functions are in S prime? That's fine. Okay, so some more examples. Okay, so this. So we have seen earlier that, so if notation, okay, just if A is a C infinity function, so everything is an Rn now. Okay. So then we have seen that phi going to A phi. So this is from D to D is linear and continuous, and that enables us to multiply a distribution. So T in D prime, A is also in D prime, AT. Okay, and AT was defined. So AT acting on phi. So this is T of A phi, and because of that observation, this definition makes good sense. But such a thing is not possible for S. Okay, so example here again, e to the n equal to 1, for example. If I take this C infinity function, and then if I take this function is in S, but e to the x square into e to the minus x square equal to 1, which is not in S. Okay, so not all we can cannot multiply a function in S by an arbitrary C infinity function in order to get back a function in S, but some growth condition should be there. Okay, so this, so you assume that, so suppose, so these functions are also sometimes called functions with slow growth. Suppose A belongs to C infinity, okay, and so D alpha Ax is less than or equal to C alpha 1 plus mod x to the alpha m alpha. Okay, for all multi indices. So you are allowing only a polynomial growth of the derivatives of A. Okay, so you are not, so you can easily check that this e to the x square does not satisfy that, because whenever you differentiate, you always get that factor e to the x square. So you cannot bound it by a polynomial. So here this condition say that you are allowing only polynomial growth for the derivatives. Okay, so then you can verify, then so you can multiply any function by A. So this is in S, is linear and continuous. So as long as only polynomials involved, so the functions in the small space, there is no trouble, because we can multiply by a polynomial and get that. That's one thing. And regarding the tempered distribution, So just one more. With this example I just stop. Okay. So suppose, so this is any measurable function. Suppose a function f satisfies integral fx 1 plus mod x minus. For some okay. So then f defines a tempered distribution. So we have already seen that all LP functions are tempered distributions. So you can also introduce. So more generally you can also introduce, instead of f you can write a measure here. Okay. So they are also fine. Okay. So instead of f you can put a measure. So this function is integrable with respect to that measure. Okay. So with this more or less we come to an end of preliminaries in the topics of analysis and Fourier transform, and next time we take up the study of Sobolev spaces, and this tempered distributions I just want to make comment. So since these are very suitable for the study of PDEs in Rn, so we can also define this the concept of Sobolev spaces we are going to introduce in the next class via the Fourier transform. So Sobolev spaces can also be described in terms of the Fourier transform that we see, and we also see the equivalence of the usual definition and then using this Fourier transform. Okay. So that will be the subject for the coming lectures. Thank you.